Welcome to this presentation on cloud-native disaster recovery with Yugabyte and OpenShift. My name is Raffaele Spazzoli. I work at Red Hat as an architect in consulting. So I help customers every day set up OpenShift and run their workloads on OpenShift. And I also am a lead at the CNCF tag storage. So it's that group of storage experts that work for the CNCF on publishing guidelines and white papers and help the graduation of CNCF projects. Today, I want to share something that we have done in the CNCF around cloud native, that we call cloud native disaster recovery. It's an approach to deal with disaster recovery. And then I would like to show you a demo of how you can do that you can create that architecture with Yugabyte. But first, let's talk about cloud native disaster recovery. It's a definition that we give. It's not something new. You could do this approach before cloud native, but it was hard to do. So our argument is that right now with cloud native approaches, you can build this architecture that we call cloud native disaster recovery, and it's easier and even more affordable to do that. To understand what it is, let's compare it and contrast it with what we call traditional disaster recovery. Traditional disaster recovery, we debated if that was the right definition to use, the right term to use, but by that we mean what you can find in the normal enterprise. Okay, not the web scalers or the cloud providers in their own internal systems, which obviously are more advanced, and not in the unicorns or the startups, but really in your average enterprise. What can you find for disaster recovery and disaster recovery processes? First, and let's look at these concerns that I have on the left. So the type of deployment of the applications. Let's think about the stateful applications, stateful workloads, because disaster recovery, it's interesting in that space. So normally in traditional DR, we find active passive deployments. So we have a database in one data center, and on the other data center, maybe we have the database is off and it's receiving copies, but it's not serving. It's receiving synchronization or maybe backup and restores, but there's not really serving traffic, so it's passive. In cloud native DR, we want to be absolutely active all the time. And then for the trigger that, that's how do we realize that there is a disaster and the disaster event occurred? Normally the trigger and the detection and the trigger is human in traditional DR. So a human decision, somebody who clicks a button and decide, okay, we are in a disaster situation, we need to trigger the disaster recovery procedure. In cloud native, we want it to be autonomous. So the system realizes that something is going wrong and reacts to it. And then when it comes to the actual recovery procedure, in traditional DR, we see a mix of manual and automated tasks, depending on how good that enterprise is. In cloud native, we want it to be fully automated. And then coming to the two main metrics of disaster recovery, right, to measure the SLA, which are RTO and RPO. So RTO is the recovery time objective. It measures essentially how long your system is down, for how long. And RPO is a recovery point objective. It measures how long of what interval of data do you lose and which transaction that were occurring during that interval of data did you lose, the interval of time did you lose. So it's essentially a measure of the data loss and the consistency of the system. For traditional DR, we have from close to 0 to hours, in the worst cases, it could be even days, before we can resume service. In cloud native DR, we want to be close to 0. And it's not 0 because there are internal health checks that need to trigger and realize that something is wrong before all the traffic can be directed to the healthy locations, but otherwise it would be near zero. For RPO, we have from 0 to hours, depending on which synchronization system we use for traditional DR. While for cloud native DR, we have exactly 0 if we are using strong and consistent deployments. So that means we never lose data. And if we're using eventual consistent deployments, we may have some data loss. And now, coming to process and ownership of the DR process, in traditional DR, the owner formally is the application team, because they normally have to publish a business continuity document. But what happens most of the time is that they turn to the storage team. They ask what the SLA, what RPO and RTO is for storage, and then they adopt all this recovery procedure from the storage team. So essentially, the storage team owns the disaster recovery process for the entire organization. In cloud native DR, it's the application team that owns the disaster recovery process for that particular application. And essentially, that's going to be driven by the middleware product that they choose. And the capabilities, technical capabilities for disaster recovery in traditional DR, they come from storage, right? It's things like backup and restore or volume replication, whether it's synchronous or asynchronous volume replication. For cloud native DR, what we noticed actually building these architectures in practice, what we noticed was that the capability that we needed come from networking. And in particular, they are east-west communication between our data centers or within our cloud regions. And we needed a global load balancer to direct the traffic to the healthy locations. Okay, so this should give you an idea of what we mean by cloud native disaster recovery and what the difference is. This is a reference architecture, very, very high level, very generalized of what a cloud native disaster recovery deployment would look like. So if we have, from top to bottom, we have a global load balancer. It's sending traffic to, in this case, 3 locations, okay? We imagine that we have a stateful workload with maybe a stateless front end. So the traffic, it's the front end, but then it goes to the workload, stateful workload. This could be a database, it could be a queue, it could be a key value store, cache, whatever it is, right? They all have to solve the same problems, which is to keep the state in sync. And they can do that having this east-west communication capability that we were talking about. So each of the instance of the stateful workload here can communicate with each of the others in a many-to-many fashion, right? And we need the ability to discover where the instances are and to open connection to them. And that's how the workload clusters up and forms these highly available clusters. And then each workload, because it's stateful, it's going to have some volume provided by the platform. These are local volume. We don't need any special capabilities on this volume. They don't need to sync. Nothing has to happen. Okay, so that's our reference architecture. This is for strongly consistent deployments, and that's why we need 3 failure domains. In this case, we have data centers, but it could be regions or whatever is your disaster recovery failure domain. We need at least 3. If we were building eventually consistent deployment, we would only need 2 data centers. Now, this is possible essentially because there is a new generation of software that is built around the CAP theorem. So this theorem is important to understand. It essentially says that between between consistency, availability, and network partitioning tolerance, you can only have two. But in reality, because we want to build a distributed system and not a monolith, we need to have network partitioning tolerance. So really the choice is between consistency and availability. And here on the right, I have a table showing some software that we have analyzed, products that we have analyzed, and the choice that they do, right? And so if they choose availability, they are eventually consistent and can be used to build eventually consistent architectures. If they choose consistency, they are strongly consistent. And then we did even more research on exactly what protocols are being used between the replicas of these workloads, stateful workload. They need the replicas to guarantee high availability. You want to have a replica of the data in each of the disaster recovery failure domain. So there needs to be a consensus and a consensus protocol and the replication algorithm between the replicas. The famous, and the most popular now is Raft, but also Paxos is fine. And then most of these databases have the ability to, or stateful workloads have the ability to create shards that allow them to scale horizontally, almost in an unlimited fashion. If they support inter-shard transactions, then they need again a consensus protocol between shards. And in this case, you can find things like the two-phase commit protocol or three-phase commit protocol. So and today we're going to see Yugabyte. Yugabyte uses Raft for replica synchronization and two-phase commit for shard consensus. Again, another view at the strong consistent deployment. This is the one that I prefer. Eventual consistency puts a lot of burden on the application because eventual consistency does not mean eventual correctness. So you only have the guarantee that the status will be eventually synchronized between the replica, but there's no guarantee that the status will be correct with respect to your application business logic. And so then the developer needs to compensate. Instead, with strong consistency, it's always correct. So if you can, my point is that you should build strong, consistent deployments. Here we see how we can do it in Kubernetes. So it's very similar to what we saw before, except now we have an ingress, okay, to enter the cluster. We have persistent volumes here provided by the platform. So switching to the demo, today what we're going to see is a deployment of Yugabyte. It's across 3 clusters in Google. We are going to use Submariner, which is a product in Red Hat, to enable east-west communication between these clusters. There is going to be a control cluster, which has been used to create these 3 clusters. It can be used to manage these 3 clusters. And then we have a global load balancer that directs traffic to Yugabyte. So, and then another detail is actually in each region we have 3 instances of T-server. So it's a Yugabyte actual server, database server, right? And they will be all clustering up into a single logical database. And then we have also the master, which in Yugabyte manages the metadata of the database. So let's stop here for a second and take a look at this scenario. And then we're gonna, as a demo, we are going to trigger a disaster situation and see what happens. But first, let's go here. So this is my console for the control cluster. As you can see, I can see my 3 clusters. They are in East 4, Central 1, and West 1 Google regions. And if I go to, I have consoles open for each of the individual clusters. You can see the master pod and the T-server pods here. Same thing in the other cluster. This is cluster 2, this is cluster 3. Let's open one just to see. It should be idling at this point because there's no, so we just see the collector, I think the garbage collector here, but nothing is happening. Do we have some other pods here that constitute the monitoring stack? And if we need, let me move this around. If we need, we can take a look at the metrics for this cluster. This here you can see only cluster 1 metrics. I don't have a way to aggregate all of the metrics. And then we can see the console, Yugabyte console. Let's refresh it. Let's go to the home. We see that we have 9 nodes, and that these T servers are distributed across the 3 regions, 3 for each region. They are perfectly balanced. So we are ready to run our demo. I'm gonna go back here, and we are going to simulate a disaster. The way we do it is we completely isolate a region by not allowing traffic to the Google Cloud network. Okay, we don't shut down the pods. We don't shut down the cluster. That would be too easy. The worst thing that you can do to a distributed system is to isolate the networks so that the packets don't just disappear and you never get an answer. And that's where the system doesn't have, that is what is the most difficult to manage for systems. So it's the right way to simulate a disaster, because the client doesn't know if the message was received, or maybe the receiver on the other side is just processing slowly of the packet was lost. So that's the right way to simulate a disaster. The other thing that we're going to do is to run a client on the database. So we're going to create a workload and then simulate a disaster and see and observe the behavior. Okay. So the client that we run is the TPCC client. TPCC is a standard performance test that you can do on SQL databases. So Yugabyte has a TPCC client that you can use to run on a Yugabyte installation to determine whether it's performing the way you want. So we're going to use that client. Today we're not interested in the performance, so we're not going to let the client run until the end. The performance are good. I have tested them, but we just want to see what happens during the disaster. Okay, so I'm going to start the clients here, and give me a second. I have to find the right. Actually, I'm going to close everything here. Okay, so this is how we run the test. The workload. I'm going to prepare because we want to start them all together. And it's going to be on 3 different terminals. Okay, so now I'm going to start the tests. The TPCC workload. It needs to warm up for 1 minute. So in the meantime, we can discuss our expectations. And our expectation is we're going to isolate cluster 3. So what happens to cluster 3 and to the cluster 3 side and the client, we don't really care. But we want to see, because that is what was hit by a disaster, right? But we care about cluster 1 and cluster 2. We would like to see that maybe they get some errors, okay, because maybe some transaction in flight don't complete correctly, but overall they continue to process, and after a while, because the cluster readjusts itself, they continue to process without errors. Okay, so I think we are almost ready. In the meantime, we can also take a look at the metrics here. You see that there is starting to be some work happening. We have something like 1,000 operations per second. And this is happening on each of the three clusters. So you can see here and here. Well, this is not ready yet, but it's going to be soon. Okay. Okay. Now I'm going to cause the disaster by isolating the network. So this is how you do it in Google. I basically create a firewall rule that doesn't let what did I do? Sorry. I create a firewall rule that doesn't let anything go through. So it's egress and ingress denial, basically denial, okay, for that particular cluster. So now it's creating the firewall rule. Okay. Pretty soon we're going to see some errors here, and for some reason, in other cloud providers, when I do this operation, I lose connectivity to this pod. Here, I don't lose it. I think Google lets any connection that is already established to continue working, but we can see that this has already gotten some errors, and some errors are happening here. So if I go to the console and I refresh it, you see that in cluster 3, all the leaders are migrating off of it. Basically, the system is realizing that something is wrong with cluster 3 and is moving all of the leaders, the tablet leaders, out of it. Now it's done. So at this point, our clients should start working normally. Sometimes there are some laggard transactions that's still failing, but overall, they should resume working normally. While cluster 3, obviously, is going to keep failing. And so this is a success, right? This is what we mean by cloud native disaster recovery. We didn't have to do anything as humans. The system realized that there was a problem and it adjusted to it, and the client, the surviving client, can continue working. Now, another property of this cloud native system is when the disaster is healed somehow. So that in this case, the third location becomes available again. Also, it should be restored to be part of the system and should restart serving traffic again without any human intervention. So I am now going to reallow traffic. Okay, and we'll see that when the system, there are a few things that need to fall into place, because the tunnel, we saw that there was a product called Submariner. The tunnel has to reestablish the connection, and then Yugabyte can see that the new nodes are still back again, and the old nodes are back again, and can start redistributing the leaders on these three clusters, on these three nodes. So if I start refreshing, you can see that it's already moving back the leadership little by little. We may see some errors on this side, but typically we don't. They continue to work normally, and the cluster is back to operating normally. So what we saw was, in summary, here's an error. In summary, we saw that during a disaster, the system adjusts itself, even if there is ongoing workloads. There can be some transaction that fails, like we said, the RTO, so the time that the system is not available is very short, but it's not zero. So some transaction may fail, but there is zero data loss. And even when the disaster situation is healed, the system readjusts itself to retake ownership of all of the available capacity that it had before. So I think at this point, well, it's slowly, as you can see, it's slowly moving the leaders to the region that has just rejoined. That is what I have for today. So if you are interested, there are some links here that I can share where you can learn how to build these architectures with your Kubernetes or OpenShift clusters and Yugabyte. And that's it for me. So if there are questions, I can now take them.